All right, welcome. Ever stop and think about how, well, this all happens? How does all the stuff your senses pick up turn into the reality you're experiencing right now? That's what we're digging into in this explainer. We're going to break down perception, that amazing process where your brain takes all this raw data and builds the world you see, hear, and feel.
So, here's the plan for today. First, we'll tackle what perception even is. Then, we're diving deep into our senses, how we organize what we see, how we judge distance, how we figure out sounds, and what's going on with touch. And we'll wrap it all up by looking at something really complex, how we manage pain. Sound good? Let's jump in.
Okay, first things first, making sense of the world. Before we can talk about seeing or hearing, we gotta get a handle on the big one, the process that makes it all possible, perception.
So, what is perception really? Well, it's not just your eyes taking in light like a camera. It's way more active than that. It's the whole process where your brain grabs all that raw info and starts organizing it, figuring out what it is, and basically building your reality from scratch.
You can think of this whole thing in three main steps. First, there's reception. That's just your senses grabbing the raw data. But then comes the really cool part, transduction. This is where physical stuff like light waves gets translated into the electrical language of the brain. It's absolutely crucial. And finally, you've got interpretation, which is where the brain puts it all together and creates what we actually experience. All right, so let's take that framework and apply it to our number one sense, vision. I mean, think about it. There's a ton of visual information hitting you all the time. To deal with that chaos, your brain has some clever rules to keep things organized.
And that's where something called the Gestalt principles come into play. The big idea here is that our brains are wired to see the whole picture, not just a bunch of random dots and lines. It's like having a set of built-in shortcuts to quickly make sense of a messy scene and see meaningful objects.
I love this idea of a visual autocomplete. So for example, there's proximity. If things are close to each other, we just naturally group them together, right? Like people sitting at the same table. Then there's similarity. We group things that look alike, like when you see a flock of birds, you see them as one group. And one of my favorites is closure. Your brain will literally fill in the blanks to see a complete shape, even if parts are missing. It's wild.
So, the big takeaway here is that seeing is not like taking a picture. It's not passive at all. Your brain is actively building what you see, using these rules to create a clean, coherent world out of what's actually just a mess of sensory noise.
Okay, but it's not enough to just see what things are. We also need to know where they are. And here's the puzzle. Our eyes see in 2D, but we experience the world in 3D. How does that even work? Let's figure it out.
I mean, how do you know how far away that car is? It's something your brain does instantly, without you even thinking about it. The secret is a bunch of tricks called depth cues. They're what help your brain turn that flat 2D image from your eyes into a full 3D experience.
And there are basically two types of these cues. You've got monocular cues, which are the ones that work even if you close one eye. You can think of these as the tricks artists use to make paintings look deep. Then you have binocular cues, which, you guessed it, need both eyes. They take advantage of the slightly different view each eye gets to give you that real, true sense of 3D depth.
This right here is a perfect example of a monocule cue. See how those parallel lines seem to get closer and closer together in the distance? That's called linear perspective. And it's the exact same trick that artists figured out hundreds of years ago to create these incredibly deep, realistic scenes on a totally flat canvas.
Pretty cool, right?
All right, let's switch from our eyes to our ears. We're going to tune into the world of sound and figure out how our brain takes simple vibrations floating in the air and turns them into, well, everything, from conversations to your favorite song.
So, how does your brain know the difference between a high note and a low one? I mean, how do you tell apart a deep bass guitar from a soaring violin? It all boils down to one simple property of sound waves: frequency.
And that brings us to the idea of pitch. Now here's the thing. Pitch isn't actually in the sound wave itself. It's our brain's perception of its frequency. So sound waves with more vibrations per second, our brain hears that as a higher pitch. Fewer vibrations, we hear a lower pitch. It's all an interpretation.
So how does the ear actually figure this out? Well, the main theory is called place theory. Inside your inner ear, you have this spiral-shaped thing called the cochlea. Think of it like a rolled-up piano keyboard. Different parts of it are tuned to vibrate at different frequencies. High notes make the part near the entrance vibrate, and low notes make the part way at the end vibrate. Your brain just looks at which part is vibrating the most and says, aha, that's the pitch.
Okay, we've done sight and sound. Now let's get physical and talk about touch.
Your skin is basically one giant sensor, and it's covered in all these tiny, specialized receptors that are constantly telling you about pressure, vibration, temperature, you name it.
Let's zoom in on a couple of these. You have Pacinian corpuscles. These guys are all about deep pressure and vibration, and they adapt super fast. That's why you feel your phone vibrate in your pocket, but you don't really feel your clothes all day. On the other hand, you have Ruffini endings. These are slow. They're the ones that tell you about steady pressure and when your skin is stretching, like when you're gripping a steering wheel.
And finally, let's talk about a big one, maybe the most complex sensation of all, pain. Here's the fascinating part. It's not just a one-way signal. It's a perception that your brain can actually turn up or down.
This is where the gate control theory comes in, and it totally changed how we think about pain. The idea is simple but powerful. There's basically a gate in your spinal cord, and this gate can either swing open to let pain signals rush up to the brain, or it can be closed, blocking them from getting through.
So how does this gate actually work? Well, you have two types of nerve fibers. Think of them as two different lanes on a highway. Pain signals travel on the small, slow lanes. But other sensations, like touch and pressure, travel on the big, fast lanes. When you activate those big, fast fibers, say by rubbing your arm, they can actually block the pain signals in the slow lanes from getting through. They essentially tell the gatekeeper to close the gate.
And this theory explains so many things we do without even thinking about it. Ever bump your elbow and immediately rub it? You're actually doing this. You're activating those large touch fibers to close the pain gate. It's the same idea behind medical treatments like TENS units that use electrical pulses, and even why distraction can work. Your brain can send signals down to help close that gate too.
So when you pull it all together, from the way your brain organizes vision with Gestalt principles to the way it can literally shut a gate on pain, the main takeaway is this. Your brain isn't just passively receiving information. It is an active, powerful artist, constantly constructing your reality from the ground up every single moment.
And that leaves us with one last, kind of mind-bending thought to chew on. If your brain is actively building your reality, then where does perception end and imagination begin?